All right, good morning or afternoon or whenever you're watching this, everybody. Today's slides are about sound and light. So what we're going to be doing today, you got the notes for today, and then you got the exit ticket. And based on some of the feedback I got from that survey, I'm going to start linking, or not linking, but I'm going to start putting the exit ticket at the end of the slides, so you guys can see them right there. You can answer them and then put them in. So we're gonna look at a few of the things I got in the feedback. Make sure you guys I only got about 30 responses, so the more the better. But I'm gonna start making some changes. There's a few things in there that I can't change just because of some other things how they play together. But I'm gonna be making a few changes, so be aware of that. So today we're gonna really talk about the speed of sound and the properties of sound. So if you remember yesterday, we talked about transverse and longitudinal waves. Sound was the longitudinal wave, and so that's kind of what we're going to be talking about. So sound is an energy that causes the molecules in a medium to vibrate. Remember, a medium can be any type of solid, liquid, or gas. So anything that has matter can be a medium. So if I knock on the table here, right, there's going to be sound waves or energy that causes the medium, the molecules in the table, to vibrate, right? So that's technically sound. Your earbuds or your computer or whatever you're watching this on, all right, it's it has speakers that causes the air molecules to vibrate, and that's creating sound that our ears can pick up. So they're the transverse wave, which is the one down here on the bottom, right? They have those areas of compression and expansion, and that's kind of where the molecules are pushing on each other. So I think these videos are really cool. I'm not going to watch them with you. It's really slow if I try and do it with you on these. But go check those out and try and figure out why, in a vacuum, right, where there's no matter, why can't you hear any sound or some of the cool things you can do with sound. So the speed of sound depends on the medium it's traveling through, right? When an object or the medium is more dense, it's going to travel faster. And that's why solids travel faster than liquids, right? So sound will travel faster in a solid than it will through a liquid, and then it will travel the slowest in a gas. And that's really it might be counterintuitive, but the faster or the more dense, the more molecules there are there, the faster that's energy is going to travel through it because it's going to be pushing on those molecules, and the closer those molecules are to each other, the faster they can transfer that energy onto each other. All right. So there's two kind of impacts on the speed of sound. What are they? Density, right? Higher density. Sorry, I had that backwards in the last slide. Higher density, lower speed, but solids still with that rigid structure are going to pass that energy along quicker. And then higher elasticity equals faster speed. So the more kind of rubbery, the more they're willing to kind of snap back to their original spot, the faster they're going to work. The speed is going to go. So the speed of sound and matter in air, it's about 760 miles per hour, and that translates to about sound waves traveling about zero point 0.2 miles per second. So in 5 seconds, sound has traveled a mile through air. If you ever see a sonic boom, or you can watch the video down here, or you can look at the picture, this jet is traveling faster than the speed of sound, right? And it's pushing those air molecules out of the way, and you really wouldn't hear anything before it, and then you get this loud boom right after the jet has gone by. It's really kind of cool. In water, sound travels about 3,000 miles per hour, and in rock, about 7,000 to 13,000 miles per hour, depending on the density and the elasticity. So it's obvious there that the speed of sound in air is really slow compared to water and rock, and it has to do with those solids, liquids, and gases. If you're I always think of lightning. You think of lightning strikes. You see the lightning, and then you hear the thunder. Right? Light travels really, really fast. So light will travel way faster than sound, and that's why you'll see a lightning strike before you hear the thunder. Same thing if you're a golfer or a baseball player or a softball player or anything, hunters even. Um, if you're far away from where that sound originates, so if you're playing in the outfield in softball or baseball, or you see somebody tee off on a golf course, or you see somebody, you know, shoot shoot at an animal, right? And you're far away, you'll probably see what happens first, right? You'll see that ball come off the tee or come off the bat, or you'll see whatever they're shooting at react before you actually hear the sound. And that's because that light travels so much faster than the sound. So your assignment today, all right, speed of sound depends on blank. Okay, it depends on the what it's traveling through. Okay, so list those two things. List in order the fastest the following: slowest, gases, liquid, solids for how fast sound travels. And then finally, a jet is traveling at 755 miles an hour. Is it moving faster than the speed of sound? Yes or no? All right, and then how much faster or slower would it need to be traveling to hit the exact speed? All right, guys, have a great day.